And two examples of this is when data comes from hyperspectral images in medical imaging. Here these images are taken not just at say 3 frequencies RGB, but at thousands of frequencies. So these are very large images. And also in genomic data, where you have a very large dimension. So one characteristic of such data is that the number of dimensions is often comparable or larger than the number of samples. And this leads to some challenges that are particular to this regime. One which is commonly termed the curse of dimensionality is the fact that the sample complexity of function approximation of certain computational complexities grows exponentially with the dimension. And for example, if you were to try to learn a function whose Lipschitz constant were 1 on a unit ball by specifying its values on several points, if you were to wish to specify the function to within epsilon everywhere, you would require 1 over epsilon to the d points, where d is the ambient dimension. It grows exponentially. On the other hand, there are certain positive aspects associated with analysis in high dimensions. These are sometimes termed blessings of dimensionality. Chief among these is concentration of measure. It is one of the chief aspects. This is the phenomenon of certain random events starting to behave like deterministic events when data is high dimensional. So for example, if you have an arbitrary probability distribution supported in a unit ball, and you take a random line from the uniform distribution in in projective space, then you take the projection onto that line orthogonally, you get a certain measure supported on that line, and that measure has a variance of 1 over dimension with high probability. So it shrinks, the variance actually shrinks as the dimension becomes larger and larger. And this can help in asymptotic analysis. We'll see some examples of the blessings of dimensionality in this talk. So one way of dealing with the curse of dimensionality is to assume that data actually, though high dimensional, lies in the vicinity of a low dimensional submanifold of Rn. And this hypothesis is called, which we'll term the manifold hypothesis, is the basis of a field termed manifold learning, which is a subfield of machine learning. And this has some rational basis in some cases. For example, if you were to deal with a number of photographs with a 10 megapixel camera of a particular object, then you can either view these as 10 to the 7 dimensional vectors, or you can try to parameterize these photographs from the position and orientation of the camera involved, which gives you a low dimensional representation of the image. And so these images can be viewed as lying in a low dimensional submanifold of high dimensional space. So in this talk, I'll discuss the question of testing the manifold hypothesis. Since manifold learning is based on this hypothesis, it's important to be able to know whether it's true or not in some definite sense. And if it were not true, then perhaps one would be more reluctant to use methods from manifold learning. So this is joint work with Charles Pfefferman and Sanjoy Mehta. And also discuss some improved sample complexity analysis of k-means. What this means is that you're interested in knowing how much data you need before which you can find a good k-means clustering of the data, which actually will make sense in terms of future data as well. And I'll also discuss a generalization of k-means where you don't have k points, which are the cluster centers, but rather you have k d-dimensional affine spaces, which are the cluster centers. So before I discuss the setting in which we'll be testing the manifold hypothesis, I'll need to introduce some complexity measures of the manifolds we'll deal with. So one of these is the notion of reach. The reach of a submanifold of Rn is the largest number such that if you take a point at that distance from the manifold, then it has a unique nearest point on the manifold to it. So for example, this curve has large reach here, and you would have to go quite far before which you get a point which has two equidistant points on the manifold. Whereas this is a curve with small reach, because you can take points here and already you have points which are equidistant from the manifold, at two different points. So the class of manifolds that we'll discuss are manifolds which are d-dimensional, have a d-dimensional volume of at most v and have a reach of at least tau, and are entirely contained inside the unit ball in Rn. So this is the class of manifolds that we'll talk about, and when we ask whether or not data is near a manifold, we'll actually mean, is data near a manifold of this kind with this sort of complexity bounds on it. So the packing number of a manifold is the largest number n, such that it's possible to pick n distinct geodesic balls of radius epsilon that are disjoint. And in our setting, this packing number is bounded above by roughly v times 1 over epsilon to the d. And the reason for this is that the volume of a ball, when it becomes small, starts looking like epsilon to the d, where epsilon is the radius, and we know that the total volume is at most v. So if you wish to have disjoint such balls inside them, the total number you can pack is at most such a number. So the framework of testing will be that of statistical learning theory. So this is the model. So we'll assume that P is some unknown probability distribution supported in the unit ball, and that x1, x2, etc. are IID random samples from P. And given an error epsilon, a dimension d, volume v, reach tau, and a confidence 1 minus delta, we wish to find an algorithm that takes a number of samples that is independent of the dimension m, and outputs whether or not there is a manifold in this class such that the expected squared distance of a random point from P to this manifold is less than epsilon or not. So this is the question we'll address. First, there are two aspects to the complexity of such an algorithm. First, there's the informational complexity, which is the amount of data you need before which you can reach such a conclusion by any means at all. And this we'll call the sample complexity. This is the number of samples needed in order to test this hypothesis. So first, I'll talk about that, and then I'll discuss the algorithmic issue of, once you have this much data, how do you actually test whether there's such a manifold. And so our first result is that the sample complexity of the task depends only on the intrinsic dimension, volume, and reach, but not on the ambient dimension. Just go through the terminology once. We'll denote by LMP the expected squared distance of a random point from P to M. And the empirical loss given a set of data points x1 to xs will be the expected squared distance when you take a random point from this empirical sample, or just the average of this distance squared from points in the set to M. And by sample complexity, we'll mean the smallest number s, such that there is some rule, not necessarily a computationally efficient rule, but there's some rule such that given x1 to xs, the probability that the output MA of the rule given on the basis of x1 to xs has a loss that is worse than the minimum possible loss by some manifold in the class of interest by more than epsilon is less than delta. So this is just the sample complexity. It's the amount of information you need before it is even possible to reach a reasonably good hypothesis with high probability. So this can be reduced to a uniform bound over the class of manifolds. This is called empirical risk minimization, because what one does here is one says that we have no access to the probability distribution except through random samples. So we would like to do some sort of minimization on the random samples and then claim that what one gets is actually good in terms of the underlying probability distribution. And in order to make a statement of that kind, it is sufficient to obtain a uniform bound over the class of interest between the empirical risk, which is the average squared distance to the manifold for given sample, and the true object of interest, which is the expected squared distance of a random point from the probability distribution to the manifold over the class. Because if that's the case, what one is saying that in this curve, where this is the space of manifolds and this is reals, is actually close to this empirical random curve, which is a function of the random samples x1 to xs. And so in order to minimize this, you can just as well minimize the random curve. So the first theorem, which is which deals with the sample complexity, says that the number of samples is actually independent of the ambient dimension. It depends only on volume, curvature, and error in this form. And the way this is proven is by viewing such manifolds as instead an epsilon net, so a number of points that kind of meshes it, and then proving a uniform bound for the larger class of point clouds, because point clouds can look very strange, not necessarily close to a manifold, while every manifold can be well approximated by a point cloud. And this is actually now related to the k-means question, because having point clouds is the same as having k-means, and that reduces to proving a uniform bound over a class of functions which is the minimum for I equals 1 to k of a dot product of some fixed vectors a1 to ak with x. So suppose, for example, you are working in 2 dimensions, then this set of functions corresponds to pyramid-like functions, because each ai dot x is a linear function. When you take a minimum of a number of these, you get something that looks like a pyramid. And we wish to find a uniform bound relating the empirical value of these functions to their true value over all functions corresponding to k distinct vectors. And the way such things are proven involve getting an upper bound on the complexity of these function classes. This complexity measure is scale dependent. It's a function of epsilon. And if you get a good bound on this, then it's good enough to get a good bound on the sample complexity. Well, this is the definition, but it's perhaps not so critical, except to know that it's a measure of how many distinct ways in which these points can be partitioned into 2 by taking level sets of functions of the class. So if, for example, k were if, for example, k were 1, then we were only looking at linear functions. Then the level sets are all lines, and you are asking how many ways can you partition the data set into 2 using lines. So the final sample complexity bound depends on, uses something called Dudley's entropy integral. And once you have a bound on this fat shattering dimension, then you immediately get a upper bound on the sample complexity. And ultimately, the way the the fact shattering dimension is bounded is by relating it to another measure of complexity which is not scale dependent. It's called the VC dimension. So while the fact shattering dimension actually was scale sensitive in that it was not enough to partition the sets into two, you had to partition the two into two with some margin of error. And here there is no margin. So the way we reduce it to VC dimension is by randomly projecting this this data where you have a margin onto a low dimensional subspace, and then using something called the Johnson-Lindenstrass lemma, which says that the additive structure of such a configuration is not very much distorted in the image space, and then using VC dimension there. The purpose here is that actually even if this is high dimensional, that space is only log s over epsilon squared dimensional, and so it's much easier to analyze the function class on when it's defined on a low dimensional subspace. So ultimately this allows us to get a bound on the fact shattering dimension, and by using this Dudley's entropy integral, we get a sample complexity of k over epsilon squared log to the 6k by epsilon. So what this really means is that suppose you have this unknown probability distribution and you want to find k good centers such that the expected squared distance of a random point from this distribution to one of the k points, the minimum distance, is small. It actually suffices to pick this many random points, which is independent of the ambient dimension, and then apply k-means to this subsample and get the centers thereby in an optimal way. And actually you can then claim with high probability that this set of centers is actually a good way of partitioning the original probability distribution. So there has been past work on k-means in this framework. There's a lower bound of k over epsilon squared proven by Bartlett, Linder, and Lugosi in '97, and an upper bound more recently proved by Maurer and Pointel that is k squared by epsilon squared. So there's a quadratic difference here. And our bound has the right dependence on n roughly. It's k over epsilon squared, some polylog factor, which comes closer to what the lower bound tells us. So this has a corollary to the question that we were really interested in by the remark that I made earlier, that every manifold of this class can be approximated by an epsilon net and then taken to actually be a point cloud, not a manifold. And the claim is that if you take S to be at least V1 over epsilon to the D, roughly, points, then you can just take those sample points and then find the best fit manifold in this class to those sample points. And you can not worry about the underlying probability distribution anymore. And you take the best manifold, and that manifold will actually, with high probability, also come close to minimizing the expected square distance of a random point from the manifold. So here is a kind of spin-off to the k-means question. Here you're actually interested in clustering using d-dimensional planes rather than points. So suppose you have a cloud of this kind and you start with k d-dimensional planes. This is like a seed, you just arbitrarily start. And then at each time step you assign to each plane the nearest point. And then you form clusters, which is preliminary clusters of this kind. And then you perform principal component analysis, which means that for each cluster you look at the inertia matrix of that point set and take the largest d eigenvalues and take that affine span of those largest d of the corresponding eigenvectors. And then you get new clusters after this, and then you repeat the same thing. So that's KD planes, and one can obtain sample complexity bounds for this too by essentially what's known as the kernel trick. So originally we were talking about these minima of linear functions. Here the loss functions, which are expected squared distance to such unions of affine planes, can be rephrased in that form after what's called the kernel trick. What you do is you take the original space and you use this quadratic map into some higher dimensional space, but the dimension doesn't figure in our bounds at all, so it allows you to get bounds. But note that here the dependence on intrinsic dimension is actually linear, and originally it was exponential. So this shows that curvature actually plays a big role in sample complexity. If you don't allow curvature, as in this case, you can get away with a much better dependence on intrinsic dimension. And issues of this kind would be important if one were to try to fit high dimensional manifolds, because it's not always the case that you want to fit only very low dimensional manifolds. So now I'll move to the algorithmic question. How much time do I have? I'm sorry, we started a bit late. So. Okay, so I have 10 minutes. Thanks. So now I'll move to the algorithmic question, where you're given n points and you wish to find a manifold in this class such that the average squared distance of a random point from among those to the manifold is less or equal to epsilon. So this is based on forthcoming work. So the outline is first note that any manifold of this class is almost contained inside an affine subspace of dimension np, where this np corresponds to the packing number at scale epsilon. And the reason for this is, what you can do if you take such a manifold, you take an epsilon net of that manifold, take the affine span of that epsilon net, which is the smallest dimensional affine subspace containing those points, and now you can orthogonally project the manifold onto that subspace. So you take a shadow of a kind. And that manifold has essentially the same reach and volume. It's clear that it's very close in Hausdorff distance, that is, no point on the manifold is very far from the nearest point on the image, and vice versa. But in addition, the curvature does not deteriorate very much because the manifold is very close to the affine subspace, because as a result even the tangent spaces turn out to be very close, and this allows one to make this conclusion. And so this actually allows one to reduce the ambient dimension m, which may be very large, to roughly the packing number, which is entirely dependent on intrinsic parameters of the manifold, namely the volume, the dimension, and the error, epsilon. Next what we are going to do is we're going to reduce the question of reduce the manifold fitting question to testing whether a given discrete evenly spread set of points actually has a manifold containing it. And then we are essentially going to exhaustively go through every such feasible point set. But the hard part here is, given a set of points which is evenly spaced, looks like it ought to have a manifold passing through all of them, roughly speaking, actually has such a manifold, because this is an inverse problem. And when you ask for a certain reach bound, you're not just asking for a certain reach bound at those points of interest, you're asking for a reach bound at every point on the manifold. So, and this question requires some new ideas. So the first step is to find a smooth vector bundle that's defined on a tubular neighborhood of the data. What this vector bundle is for every point defined in this, for every point in a neighborhood, you have to assign a vector space of dimension equal to the codimension of the manifold. So in our case, n minus d, which kind of looks like the orthogonal space to the tangent plane near that manifold. It's a kind of normal bundle. And then use this space to define locally defined functions whose common zeros are actually the manifold. So you're defining the manifold as the common zeros of certain locally defined functions. And then one has to estimate the smoothness of such a resultant manifold, which is done using the implicit function theorem. So here is one key lemma that goes into this. So both the vector bundle and those functions involved are derived from a single function which is locally defined. So suppose you take a small section of this, a small part of this manifold you're interested in, and you make a small cylinder over there. Since you roughly know what the tangent space is, you can take a d-dimensional ball that's roughly in the tangent space and an n minus d dimensional ball that's roughly in the normal space, and look at the cross product. So you have a cylinder, and we look at how to specify the manifold within that cylinder. And the way we'll do it is we'll first define a function which has the property that it looks a lot like the squared distance to the d-dimensional base. So in it roughly speaking measures the squared distance to the d-dimensional base, but not quite. There is a rho squared here which allows for curvature. And then once you have that function, we'll define the vector bundle as the large eigenspace of the Hessian of the function at different points. So since this function grows quadratically in the normal space, roughly, the Hessian has a large eigenspace that's like the normal space. And that's how we'll get the vector bundle. We'll look at the Hessian, we'll take the large eigenspace. And now, in order to locally define those functions whose common zeros are going to be the manifold, we'll look at the set of points such that the gradient of this function is orthogonal to that space. So when you say that something is orthogonal to a n minus d dimensional space, you essentially get n minus d constraints. And that's right, because if you're trying to get a d-dimensional manifold in n space, you do locally need n minus d constraints. So this is the scheme, and we're going to get a disk bundle using these normal spaces. The reason it's a disk bundle is that if you start going sufficiently far, simply because of the reach condition, you're going to start having these self-intersections. So we don't want to go too far. And one can, in addition, bound the curvature of this bundle. And so this is roughly an important part of it. And in the end, we have a theorem which has the following form. There is a control constant c depending only on the dimension d, and an algorithm that uses n log n exponential of some intrinsic parameters number of operations on only real numbers, which ultimately will answer yes if there actually is a manifold of the kind we were looking for, and answer no if there is no manifold even of a much richer class. So there is some gap over here that we believe we can improve, but this is the nature of the theorem. It says that if there is no manifold which possibly has somewhat larger curvature, then we'll say no. If there is a manifold of the kind we were interested in, we'll say yes. So that concludes my talk. So to summarize, we spoke about the sample complexity of testing the manifold hypothesis and show that it's independent of the ambient dimension, and discuss some algorithmic implications of k-means and k-d planes, and also spoke a little about how one can fit more general manifolds to data. So thank you. Manifolds to a fixed set of data, but the first part showed that the latter question is actually good enough to actually fit to the distribution. So the first part showed that, yeah, that was the role of the first part. If you want to fit to a distribution, it's good enough to sample and fit to the sample. And the second part was about fitting to the sample.
Okay.
Thank you.